Hello, and welcome to today's session on inferential statistics. Today we're going to be talking about the process of drawing an inference about a population based on a sample. So you can see that the word inference is at the root of inferential statistics. We're trying to draw some conclusions. To do that, we're going to be relying very heavily on frequency distributions and also on z-scores. And we'll do them in that sequence. Frequency distributions first, we'll give you an overview of those, and there will be some review along the way. And then we'll talk about the new concept of a z-score, which, as you will see, is very much like a standard deviation. And then we'll see if we can build on that and talk about the relationship between z-scores and percentile rank. Before we begin, though, please make sure, as always, that you have the PowerPoint lecture notes printed and in front of you so that you can take notes along the way. Okay, let's see if we can begin by talking a little bit about frequency distributions within the context of our research cycle that we see here. As always, we remind ourselves that as psychologists, we're interested in the science of behaviors, thoughts, and feelings, and those would constitute the real-world phenomena that we have shown here schematically. From that, we abstract or take our samples and make some operational definitions to get something that's manageable, a research representation. And then once we have that representation, we can use any of a number of different kinds of methodologies, including survey methods, observational methods, or experiments, to generate some kind of research results. Today's session will be focusing on data analysis. We'll be talking about frequency distributions and the z-scores and their corresponding percentiles that will allow us to draw some conclusions or inferences about a population from its sample. In a future video, we'll also talk about evaluating hypotheses along these lines as well. After we have our results, we hope that this will generate some kind of research conclusion that will generalize back to the real-world phenomena of behaviors, thoughts, and feelings. Okay, so we can say then that we'll begin our conversation with frequency distributions by reminding ourselves that many naturally occurring phenomena are well described by a bell-shaped curve. And the bell-shaped curves go by different names. We can think of them as normal distributions, and they're frequently called that. And we can think of them as Gaussian distributions after Johann Carl Friedrich Gauss, who was the German mathematician who lived in the late 1700s, early 1800s, who found this particular curve, and it's really quite central to so many different sciences, including the science of psychology. In case you're interested, here's a wiki on Gauss that I think you might find intriguing. Okay, so here's the shape that we're talking about, and you can see that even though there's some variation across these shapes, they all conform to what we would call a bell curve format. Some of them are broader, some of them are narrower, but they all fit the general idea of a bell curve. What's important about this is that we're going to make a connection to other kinds of shapes that might have some variability and yet are still identified as that particular kind of shape. Specifically, we can think about a right triangle. And you spent a lot of time in high school learning about right triangles and the properties that they have. And you know that the Pythagorean theorem, a squared plus b squared equals c squared, is a formula that can be applied to any kind of a right triangle. It can be a really large triangle, a really small triangle. It can be a triangle of intermediate size. It doesn't matter what the particular proportions might be. So long as we have a right triangle, then a squared plus b squared plus c squared is going to describe that. It turns out that there's a very similar kind of relationship here for these bell-shaped curves. And that is to say that each of these bell-shaped curves has a formula associated with it. And we won't be talking about that specific formula today. It's actually quite involved and took a mathematical genius like Gauss to discern that formula. But just like a triangle has certain properties that are relatable to its mathematical formula, so it is with these Gaussian shapes or bell-shaped curves. Okay. All right, the width of the normal distribution is an indication of the standard deviation. So if we can harken back just for a moment to what we described previously in our conversations about descriptive statistics, we said that we typically are looking at some indicator of central tendency, which might be a mode, median, or mean, and some indication of dispersion, and it might be something like a standard deviation. And these are very important properties of Gaussian curves. Fat distributions, fat Gaussians, have big standard deviations, and thin distributions have smaller standard deviations. So here they are again, and we could ask a very simple question: which distribution has the largest standard deviation? So hopefully, by looking at this, you'll immediately eliminate this one because it's too narrow, and you might guess that it's perhaps this one or maybe that one. This one might look just a little bit fatter, so it has a really large standard deviation. One other connection here between these shapes and the formulas that underlie them. We've already talked about the relationship that the Pythagorean theorem has to right triangles. We can say that there are other examples that you might be very familiar with where something about a shape is well tied to its mathematical formula. One very salient example would be something that you might have had in 7th or 8th grade, and this would be the linear equation, y equals mx plus b. Most of us learned that linear equation, and you might recall that the m component controls the slope. We can have a relatively steep slope or a shallower slope. That's what the m in y equals mx plus b does. The b in y equals mx plus b controls the y-intercept. So for a given slope, we can have a higher y-intercept or a lower y-intercept. And so we have those two parameters or descriptors inside of a simple linear equation. The same thing is true for Gaussian curves. A Gaussian curve also takes two parameters. It takes a mean and a standard deviation, which you and I are very familiar with from our conversations about descriptive statistics. So we can say then that if we were to look at the parameter that was controlling the standard deviation of this curve, it would be much smaller, and here we'd have a relatively large standard deviation. The mean, interestingly enough, moves a particular bell-shaped curve to one side or the next. So as it's moving to your right, we're having higher means. As it's moving to your left, we're having lower means. So its relative position, centralized on the x-axis, is driven by the mean, and its width is driven by the standard deviation. Just like the y-intercept and the slope control those two features of a linear parameter, or a linear equation, we have the mean and the standard deviation controlling where a particular bell-shaped curve might be positioned on its x-axis. Okay, we might ask this question: which distribution would have the smallest error bars if we were to plot the means and error bars on a bar chart? Okay, so this is usually something that some students find a little tricky. They can understand this kind of a graph, and they can understand this kind of a graph, but they sometimes have trouble seeing the connections between them. So let's see if we can unpack this graph first, and then we'll toggle back and forth between these two diagrams. Okay, so here in this graph, we're plotting motion sensitivity as indexed by something called d prime as a function of Q condition. And we have 3 levels of this variable. We don't even need to know what Q conditions are to see that we have 3 levels, and we don't even need to know what motion sensitivity is to see that that's our dependent variable plotted on our ordinate, and the independent variable is plotted on our abscissa. As you will recall, the dependent variable is what we measure, and the independent variable is the variable whose effect we seek to know. Okay, so what might be a little bit new for us is that some students haven't always seen these bars. Okay, so let's see if we can unpack what those are. These are called error bars, and they reflect what we might call statistical error. Statistical error doesn't mean that we've made a mistake. It means that we have some margin of variability. We have some dispersion. So this harkens back to our conversation on descriptive statistics, where we might begin to describe a data set in a particular condition by, for example, drawing the motion sensitivity all the way up to the mean for that condition, in this case 0.5, and indicating some dispersion by having these error bars go plus or minus 1 standard deviation. And it might be that this is something like a 3% change around that 0.5 mean. Okay? So we can think that we can go up or down by 1 standard deviation. The average extent to which a score departs from the mean is the standard deviation. Okay? Now, over here we have another Q condition. This is the no Q condition, and it has a slightly higher mean, but it has a margin of error or a standard deviation of about the same amount, maybe 3 percentage points on this graph. And then we have in the invalid Q condition much less motion sensitivity. Maybe that's at about 0.3-ish, and then again we have something like a 3% margin of error or standard deviation. In various graphs, you, as the author of the graph, have complete control over whether you want to plot as your error bar a standard deviation, or its near cousin, a standard error, which you might remember is the standard deviation divided by the square root of n, where n is the number of observations that we have. You could even make these bars correspond to other measures of dispersion, maybe the range, or, as we'll see later on today, the interquartile range. What some students have trouble doing is connecting this kind of a graph to this kind of a graph. And the main idea here is that we can look at how wide or narrow a particular distribution is, and remember that the wider distributions, the fatter distributions, have larger standard deviations, and that's because their scores are varying more on average than would be the case in this smaller deviation Gaussian, where we have less variability. And And if we come over to here, we can see that you can imagine extending these out that way if we had a wide Gaussian, or shrinking them down a bit if we had a narrower Gaussian. So hopefully you can see the connection between those two kinds of graphs. Okay, let's see if we can go a little further to develop our intuitions about standard deviations. I'm going to show you in the next slide a list, in fact 4 different lists of numbers, and these all have something in common. They all have a mean equaling 5. So they all have the same central tendency in the sense that they all have the same average, but they're going to differ from each other in dispersion. So just by looking at the lists, you should be able to tell which one is going to have the fattest Gaussian, or the biggest standard deviation, and which is going to have the narrowest Gaussian, or smallest standard deviation. So here are the lists, and I apologize if this is too small to be seen on the video, but hopefully you've got the PowerPoint lecture notes printed in front of you. You can see very clearly that these are not going to have the same standard deviations. So in class, we'll ask you to report which one has the largest standard deviation and which one has the least standard deviation. Okay, normal distributions are important in science because they allow for standardizing across experiments and disciplines. Really a very interesting idea that we can use these bell-shaped curves, and as you'll see shortly, we can use z-scores to essentially make apples to oranges comparisons in a way that's really scientifically rigorous. Let's give you some other examples. IQ scores, SAT scores, and height. These are just a few of the variables that are well described by the bell curve. These are said to be normally distributed or Gaussian distributed. Okay? In this table, we have a few different variables listed in each of the rows, and we're going to, for the moment, ignore the z-scores, but we'll come back to that concept later. In these first 3 rows, though, we'll take a look at what the variable is, we'll take a look at its mean and its standard deviation. So the descriptive statistics. And this first one is one that I'd really like you to memorize. So please pay attention to this and please jot it down. We'd like you to memorize for many future questions in this class that the mean IQ score across, for example, the United States is 100. The standard deviation would be 15 IQ points. Okay, so that would be true for the overall US population. We can look at other variables too. We can look at the SAT test, and we would have a mean of 500. We would have a standard deviation of 100. Just so you know, it turns out that on the SAT, we have a range that goes from a low of 200, you get this beautiful bell shape, and then it goes all the way up to 800. So what's interesting about that is that we have something like a 6 standard deviation range. We go from 200 to 300 as our first standard deviation, from 300 to 400 as our second, 400 to 500 brings us up to the mean, and that's 3 standard deviations. And then going off to our right, from 500 to 600 gives us our 4th standard deviation, 600 to 700 our 5th, and finally 700 to 800 is our 6th standard deviation. So we have a 6 standard deviation range in the SAT centered at 500, and the step sizes are 100 SAT points. We can go to a very different kind of measurement, a physical measurement like height. And we can talk about the average height of women, which might be Gaussian or bell-shaped. And according to this table, the average height for women would be 160 centimeters, plus or minus 5 centimeters. And that's how we can think of the standard deviation. It's our plus or minus number, so to speak. It gives us the average extent to which a score will be departing from the mean. Okay. So not all distributions are symmetric. So far we've been talking about these beautiful Gaussians that are symmetric. It's one of their properties. But sometimes we have these asymmetric distributions, and some of them are said to be positively skewed. These have tails off to their right, to the positive side of the axis. Others are said to be negatively skewed, and these have tails off to the left or negative side of the axis. Okay, and to put this into context, we'll just see if we can walk through this fun exercise. Here's the thinker, and this is a very famous statue by Rodin. And here we have somebody striking a very contemplative pose. This is Michael Jordan, as you might know. He's a very famous basketball player from the 1980s and 1990s who really made a lot of money playing basketball. But here's our question for the thinkers. Thinking about majoring in geoscience? Okay. Did you know that the average, I'm talking about a mean here, the average geoscience major who graduated from the University of North Carolina in 1984 earns about $600,000 annually. Sounds like a great major, right? On average, we're earning $600,000 a year. Wow, pretty impressive. Okay? But there's something wrong with this picture. And this brings us back to the idea of skewed distributions. In this case, we have a positively skewed distribution. which, as we said a moment ago, has this long tail off to the right. One typical example that's given for a positively skewed distribution is going to be the salary distribution. So in the example that we had just a moment ago, Michael Jordan, who did really, really well as a basketball player and made a lot of money, happened to have been a geosciences major when he was at the University of North Carolina in the early to mid 1980s. It would have been a relatively small group of people who would have graduated from that school in geoscience as a major. And so you can imagine that one really, really well-paid geoscience major, like Michael Jordan, the basketball player, might be skewing that distribution. He might be way out here, whereas more typically, the other geoscience majors are going to be down here on the salary distribution. What's critical about this is that when we see these skewed distributions, we have a new mantra that we have to repeat, and that mantra is that the mean follows the tail. Okay? So out here, we have the tail, and the mean gets drawn away from this modal component out this way. The mean gets pulled most dramatically relative to the other two measures of central tendency. So we have this extreme score, and you might remember that the mean is actually sensitive to every score in the distribution, even those weird outliers that are all the way here. In our earlier example, the most extreme outlier would be somebody like Michael Jordan. So it's a little bit misleading, as you might imagine, to say that the average person from that particular graduating class earned $600,000 a year. It is statistically correct, but it's misleading because we have such a skew in our distribution. Okay? So again, we can state that mantra a couple of different ways. The mean follows the tail. If you like to say it this way, you might note that the mean chases the tail. So a salary distribution is shaped like that. In psychology, many reaction time experiments tend to form this kind of a shape, where generally speaking we have relatively fast responses, where reaction time is relatively low. But on a few trials, maybe we sneeze, or maybe we zone out informally, and we have a much longer reaction time occasionally, and this gives us some outliers down on this side. So frequently in psychology, reaction time data sets are characterized not by a perfect Gaussian, but rather by a positively skewed distribution. Okay? We're also going to learn in just a few videos about a new statistic for us. It's called the chi-square statistic. And the chi-square statistic will have a particular kind of shape that is very much like the shape you see here. It'll be positively skewed. After that, we'll learn about yet another statistic called the ANOVA. And the ANOVA distribution, just like the chi-square distribution, is going to be positively skewed. Okay, let's see if we can flip it around and talk about a now negatively skewed distribution. So here you can see that on the left-hand side of this x-axis, we have this long tail, and then it begins to approximate normalcy, but it's really departing from normalcy because of this skew. And we can say once again that the mean chases the tail, so the mean is drawn furthest away from the mode, and the median, as always, will be in between the mean and the mode on these skewed distributions. And hopefully that's intuitive to you for two reasons. First, the mode is always easiest to find. It's just the highest score. So it's really easy to pull out. And we know that the median is going to be somewhere in between the two, and that's easy to remember because the median on a highway separates things. Here the median is separating the mean from the mode. Okay? So we can use our mantra, again, which is that the mean chases the tail, and in this case it's chasing the tail out to the left. We might ask ourselves about a few different commonly observed examples of these negatively skewed distributions, and one that might be of great interest to students is that grades on exams tend to be negatively skewed. That is to say, there are relatively few students that get absolutely perfect scores way up here, but a lot of students are scoring maybe in the B range or C range. Fewer students are scoring Ds, and among those who are scoring Fs, fewer and fewer of them are really close to 0. Okay? Typically, they can get up at least this far, even if that's not a passing grade. Lots of Bs and Cs in relatively few As. So grades make a great example of a phenomenon that is negatively skewed. Another example would be for humans' gestational period, or gestational duration. This is the length of time that a fetus will be in the mother's womb. For most humans, the modal tendency is going to be something like 9 months or so. But it's not that unusual for it to be a little bit longer, like maybe 9 months and a week, 9 months and 2 weeks, 9 months and 3 weeks. But as you start approaching the 10-week mark, usually doctors will induce labor, and usually the doctors wouldn't need to because that's happening with such low frequency. On the other extreme, it's relatively rare that the baby will go substantially less than that interval. And you can see that that frequency tends to fall off as we get back closer and closer to 0. Okay, so that's an example of another negatively skewed phenomenon. Okay, why don't you take a moment to stop the video and make a note of what was really clear and what was less clear. Okay, welcome back. And now we'll begin talking about z-scores. If we have a normally distributed or Gaussian distributed variable, maybe one that's pertaining to behaviors, thoughts, or feelings, and if there's not too much skew, not too much negative skew, not too much positive skew, it can be helpful to describe a particular score either by its original unit of measure. For example, height is measured in centimeters, weight is measured in pounds, intelligence is sometimes measured in terms of one's IQ score or the number of IQ points that you can accumulate. We get the idea. Okay? If there isn't too much skew in there, we can express the scores either in their raw values or according to a z-score. A z-score is a standard deviation from the mean. Let's all say that together. A z-score is a standard deviation from the mean. Okay, I knew you could say it. That's going to be an important mantra for the rest of this semester, so it's good that we really get that idea down. Okay? We can ask, why is it the case that z-scores are important? And as I alluded to a moment ago, what's really nice about z-scores is they can allow us to compare across very different dimensions. We can compare, for example, relative height to relative IQ. We can compare relative depression levels to relative salary levels. Salary is measured in dollars or some other unit of money. Depression might be measured by an indication of a response on a depression inventory, like the Beck depression inventory. Height might be measured in centimeters. These are very different units, but we can get to a dimensionless measure by using a z-score. It's dimensionless because we simply are expressing the number of standard deviations. Okay, let's see if we can learn how to compute by hand a z-score. A z-score, again, is simply a standard deviation from a mean, and we'll see if we can use IQ as a simple example. So if the standard deviation of the IQ score is 15 points, okay, and you might remember that the mean was 100, okay, then one z-score would correspond to 15 points above the mean. Two z-scores would be 2 times 15, okay, or 30 points. 3 z-scores would be 3 times 15, or 45 points. You can have negative z-scores because half of the scores in any given Gaussian distribution are lower than the mean. So if we have minus 2 z-scores, we would take minus 2 times 15, or minus 30 points, which is to say below the mean. Okay? Okay, so here's the formula that you'll need to know for the rest of the semester. And I would encourage you to memorize this. You probably only need to memorize one of the 2 variations here, if you can algebraically rearrange the first to get to the second. Okay, so here's the formula for computing z-scores given a particular raw score. So we're looking for a z-score, a certain number of standard deviations from the mean, and these can be expressed as integers, but they can also take fractional values. So here's our z, and what we do is we take the raw score, we subtract from it the mean, and then we take that quantity or that difference score and we divide it by the standard deviation. Okay? Now you can move those terms around algebraically. You might imagine that if you wanted to, for example, solve for the raw score, what you would have to do is multiply by the standard deviation. So we'd take z times the standard deviation, and that's what you see over here. We'd also have to get rid of this negative mean by adding the mean to each side of the equation. And this harkens back again to what you might have learned in 8th grade algebra or thereabouts. You might have learned that according to the golden rule of equations, you can do anything you want to the left side of the equation as long as you do exactly that same thing to the right side of the equation. So these 2 variations that we see are simply algebraic versions of each other. There's nothing particularly special about one of them more so than the other. Sometimes we're looking for a z-score and we have this information. Other times we actually do have z information and we want to derive a raw score. Okay? Let's do a couple of examples just to make sure you're on board with this. If the mean IQ is 100 with a standard deviation of 15, and if I've got a friend named Larry who has an IQ of 130, the question is, how do we express Larry's IQ in terms of z-scores? We'll let you think about that for a moment. Okay, why don't we go on? If the z-score associated with Craig's IQ is -3, okay, so just to make that really clear for you, that would be 3 standard deviations below the mean, then what is his IQ score? You can take advantage of the formula that we had seen on the previous slide, and see if you can come up with Craig's IQ score. Okay. Note, if the standard deviation equals 0, then the z-score is undefined. That is to say that from this formula, if we do have a 0 over here for the standard deviation, which would mean that we have no variability at all in our data set, we would be dividing by 0. And as you might remember, division by 0 is undefined. Okay, so why don't we have you pause the camera one more time, or pause the video recorder one more time, and see if you can jot down what was clear and what was less clear about that. Okay, welcome back. We're now going to try to connect this new idea of z-scores to something that you might recall from a previous discussion, and that's the idea of percentile rank. We can think of percentile rank as the percentage of scores at or below a given score. And that's going to be very germane for our conversation about this bell-shaped distribution, z-scores and percentile rank. For any Gaussian distribution, 34% of the population falls between 0 and positive 1 on the z-score scale, and another 34 falls between 0 and negative 1, as you can see here. So one of the nice features about a perfect Gaussian is that it has these mathematical properties, just like a linear curve has, or a linear trend has mathematical properties, a right triangle has mathematical properties. One of the mathematical truths of a Gaussian distribution is you always get the central portion adding up to 68% of the overall population. So if we go to plus and minus 1 standard deviation, we get 34 and 34 adding up to 68% of any given Gaussian distributed variable falls within 1 standard deviation of the mean. It's a really nice property of these Gaussians. Okay, here's a question. What percent of the population falls between z-scores of 0 and negative infinity? We'll give you a moment to think about that. Okay, so here are the z-scores. Remember that we can have positive z-scores or negative z-scores, and the question asks us to think about the portion of the population, or the percent of the population, between the z-score that's at 0 and negative infinity, which is all the way out this way to the left. Okay? Hopefully you would have the intuition that that simply divides the entire population in half, and so half would be 50%. So 50% falls between this point and that point. Another way of thinking about this is the area under the curve. Some of you are familiar with calculus, and specifically with an area or a topic within calculus that is called integration. And if we integrate or add up the total area under the curve between one point specified on the right and some other point specified on the left, we get some notion of just how much of that curve is occupied in that range. And in the world of statistics, that typically corresponds to a probability. So if we were to pick items randomly from this full distribution, 50% of them are going to be down this way. We can think of the area to the left of that z-score equals 0 as corresponding to the probability. In this case, it would be a 50% probability below, 50% probability above. Okay? All right, see if we can take another question about this distribution. If your z-score is 0, what's your percentile rank? Remember, the percentile rank is the percentage of scores at or below a given score. We'll let you think about that for a moment. Okay, hopefully you came up with the same answer. If you're here at the 0 z-score, you're at the 50th percentile. Half of the scores are at or below that particular score. In this case, the score is expressed as a z-score. Okay, here's one more question. If your z-score is positive 1, I'll point to that over here, what's your percentile rank? Okay, hopefully you came to the number 84. And the reason that we come to that number is we know that we have 50% to the left of this point, and we're now going up one more standard deviation, which adds another 34% of the population. So 50 plus 34 gets us to 84. So now we're at the 84th percentile when our z-score is positive 1. Again, just to remind you, what's really wonderful about this is that this will be true for any variable. It doesn't matter whether it's height or weight or IQ, or physical attractiveness, or depression scores, anything that's Gaussian shaped. If you know that a particular score is at the positive 1 standard deviation or z-score, then you know it's in the 84th percentile. Okay, let's now ask about changing that z-score from 1 all the way up to 2. We'll let you think that one through. What percentile rank are we at? Okay, hopefully you can see that we're at the 98th percentile, and just 2% of the scores would be higher than that. 98% of the scores are at or below the z-score of positive 2. Okay? Now here we get just a little bit tricky. We're going to ask you to do just a tad of mental gymnastics. We're now going to try to relate this to something that we learned earlier, which was the IQ distribution. Remember that the IQ distribution had a mean of 100 in raw scores, and it had a standard deviation of 15 IQ points, again expressed in those raw scores. Now what we'll do is begin to mix and match the raw scores with the z-scores. So the question here is, if your IQ is 85, what's your percentile rank? Okay. We'll let you think that one through. Hopefully you're reasoning along this way. Remember that the mean IQ score is 100. Remember that the standard deviation is 15. If we do 100 minus 15, we would be at 85. That's going down by 1 standard deviation. And hopefully you can see that we have this 14% and another 2%, so a total of 16% would be at or below this -1 z-score, which corresponds to an IQ of 85. Why? Because the mean for the IQ distribution was 100. The standard deviation was 15 points, and that brings us down to 85. Okay? All right, so by convention, if a score is in the top 2.5 percentile, it's way up here, or the bottom 2.5 percentile, way down here, psychologists consider that score to be significantly different from the mean. In fact, that's a standard adopted by lots of scientists, not just by the subset of scientists that are also psychologists. Many scientists use a 0.05 as a convention. To be fair, you should know that that is actually an arbitrarily selected standard that we've used for many decades in the sciences, but other folks could have drawn a very different cutoff point. We typically use the most extreme 5%, and remembering that the curve is symmetric, we'll take half of that 5%, or 2.5, and put that up this way, and 2.5% down that way. Okay, so suppose we want to know what z-score is associated with, say, the bottom 2.5% of the population. How to begin doing that? Well, just by using our intuitions and by eyeballing the diagrams that we've had before, we would know that it would have to be somewhere near 2, because here we know that we're looking for the 2.5 percentile, okay? And we know that that's got to be pretty close to this last 2%. So it might be just a little bit shy of the -2 mark. So not all the way to -2 would be a ballpark estimate. What we can do, though, is we can get a lot more precise. We can actually go inside of Excel and take advantage of a new command. This command that we're going to learn does something very interesting. It takes in a proportion or a probability, and it puts out for us a z-score. Okay? And this command syntactically is all about putting in the equal sign, as is always the case, and then norm sinv is the name of that function. It's an unusual name. Let's see if we can understand what this stands for. Norm sinv is an abbreviation for the normal standard inverse. Okay? So we have different kinds of normal curves. We have an IQ normal curve, we have a height normal curve, we have something called the standard normal curve. The standard normal curve is centered at 0, so its left half is going to be in the negative range, and its right half is going to be in the positive range. Its mean is right at 0, and we have a standard deviation equaling 1. And you might remember from earlier in this video, we talked about how just like all triangles have this property of that adheres to the Pythagorean theorem if it's a right triangle, and how all linear functions have a slope and a y-intercept. We can say here that if we have a normal standard deviation, its two parameters are the mean, which would be 0, and the standard deviation, which would be 1. Okay? Okay. So in just a moment, we'll flip over to Excel and we'll show you a couple of examples where we can put in some proportions and pull out the corresponding z-scores. So remember that this function, this norms inv function, is just like any other function. It's a rule for turning one number into another number, or maybe for turning a range of numbers into another number. Just like the average function takes in a range of scores and puts out one average, so it is with the norms in. We put in a probability or a proportion, some number between 0 and 1, and we get out a z-score. Okay, just to convince yourself, we'll stick in some known values in just a moment. We'll put in a 0.5, and we should get out a 0.84, and we'll come out with some pretty prototypical z-scores in just a moment. Okay? Here's the 50th percentile. Again, where would that be in z-scores? We'll have you think that through. How about the 84th percentile? Where would that be in z-scores? We'll have you think that through. Okay, we'll do it in Excel in just a moment. There are other times when we want to know other kinds of centiles. Typically the 25th and the 75th percentiles are important for us because they're the interquartile range. They take the full distribution and they divide it into quarters. So when we want to know what the bottom quarter is, we're looking for that cutoff at about the 25th percentile, or exactly at the 25th percentile. And when we're looking for the highest quartile, we're going to have a cutoff that begins at the 75th percentile. So we might want to know what z-scores are associated with the 25th percentile and the 75th percentile. Okay? One example that we might use here is that frequently SAT scores are reported that way in the different kinds of rating scales that you might get for colleges. Colleges sometimes want to rate themselves or even rank themselves against other colleges, and they report their 25th and 75th percentile SAT scores to show just how competitive their students are academically. Okay? Here's a graph of the interquartile range, the 25th percentile and the 75th percentile. So here's our Q equaling a raw score value of 4.5 in this particular case, and here it is at 8 at the 75th percentile. That's the top 25th percent, the bottom 25th percent, and in between we have exactly half the population, and that would be 3.5 points on this particular scale. Okay. So using norms inv as a command in Excel, we can find the z-scores that correspond to the 25th and the 75th percentiles. Okay? We can also do that backwards. Okay? So what we can do is sometimes instead of having a proportion and trying to derive the z-score, we might have ready access to the z-score, but we want to know the corresponding proportion. So we can do the inverse function from the norms inv, and that is going to be called the norms dist function. Again, as always, we'll start with an equal sign. We put in norms s dist, and that's the normal standard distribution. And in this particular case, we're going to take in a z-score. That's going to be our input, and what we'll put out is a proportion, or if you'd like, a percentile rank. Okay? All right, and here are a couple of examples. What percentile rank is associated with a z-score of -2? Okay, the norms dist function would tell us about that. And here's a really good one for you to think about, again, to end with just a little bit of mental gymnastics. What percentile rank is associated with an IQ of 145? Okay? Here's a little hint and a little bit of a reminder that the IQ distribution has a mean at 100, so that's where the 0 z-score is, and it has a standard deviation of 15 IQ points. Okay, so we'll let you think that one on through. Okay, just to give you a feel for what this looks like inside of Excel, I'll call this up, and we'll do a few exercises, first with the norms in function, and then with the norms dist function. So here, we might look at the proportion of interest, and we can put in any proportion we want, and we'll try to get the corresponding z-score. I realize you can't see this particular formula bar over here, so I'm going to make it really large just for a moment and remind you of the syntax inside of Excel. So here's proportion. We'll say that we're at the 75th percentile. We'll use proportion and percentile rank synonymously. And then here's the z-score, and here's the formula. Equals, okay, which will always get the computation going. Norm, this is the normal distribution or the Gaussian or bell-shaped distribution. Of the many, many different kinds of Gaussians, this is the standard, which is centered at 0 and has a standard deviation of 1. And we're using the inverse function. We're going to take in a proportion and spit out a z-score. Okay? So let's go ahead and do that. And if I put in a proportion of 0.75, I wind up with a z-score of 0.67. So that's 2/3 of one standard deviation, approximately. Just to remind you of some other items that we talked about, you can have a proportion equaling 0.5, and that would be the 50th percentile, and that corresponds to a z-score of 0. So 0 is right in the center, negative z-scores were this way, positive z-scores were that way. If I increase my proportion away from the 50th percentile to something like, for example, the 84th percentile, I should get a z-score at least near 1 within some rounding error. The 84th percentile is well approximated by the z-score equaling 1. I can go all the way down to the equal and opposite side, the 16th percentile, which would be 0.16, and I'd get now a negative 0.99. Okay. If I want to go up to the 25th percentile, I put in 0.25, and I get a negative 2/3 of a standard deviation, a negative z-score, here negative 0.67. Again, because the bell curve is symmetric, this is going to be, if this were 0.75, then this would be positive 0.67, as we did just a moment ago. Okay, and you see how that works. We can take a really extreme score. Imagine that you're in something like the 0.999 percentile. You're going to be 3 standard deviations above the mean. Your z-score will be positive 3. Okay. Let's see if we can do an example of the inverse function. And just to remind you about inverse functions, you might recall from your earliest days in grade school that we can think of addition and subtraction as being very complementary functions. You can add something, add 3 to something, and then take 3 away. Addition and subtraction are complementary in that manner. Same thing is true for multiplication and division. We can scale something up by some multiplicative factor and then divide it down by that. The same thing is true for exponentiating, maybe squaring something and then taking the square root. We can now think of the same for z-scores. We can stick in a proportion and get out a z-score in the norms in function, or we can do it the other way around. We can do it backwards. We can stick in a z-score and come out with a proportion. So here, if my z-score is positive 3, my proportion is 0.999, which is to say the percentile rank is 0.999. And if I do a minus 3, okay, oops, excuse me. Okay, then I get the complement of that number. I'm in a very, very low percentile. I'm at the fraction of 1 percentile. Okay, if I go back to a z-score of 0, that puts me right in the center of the distribution at the 50th proportion or the 50th percentile. If I put in something like a z-score of 1, that should get me pretty close to 0.84 and so forth. Okay, so I would encourage you to practice this, and just to remind you of what that syntax looks like, here it is. This will be equals norms dist, and we insert whatever value we have here in cell A2, and we are able to come out with the proportion associated with that z-score. As our final slide, what I'll ask us to think about is a simple chart in which we talk about what the function is inside of Excel, the function name, norms in and norms dist, and we remind ourselves of what goes in and what comes out, just to keep all of these things straight. So in the norms in function inside of Excel, and I'm even going to add the equal sign over here, because if you try it without the equal sign, Excel will not perform the computation for you. We stick in a proportion, which is also a probability, which is also a percentile rank, and we get out a z-score. And then we can do the inverse of that. We can take the norms dist function, we put in a z-score, and we get out a proportion, a probability, or a percentile rank. Okay, that was a lot. I hope that you enjoyed that presentation, and more importantly, I hope that you'll jot down what was clear to you and what was not so clear to you. It's important to do both of those because when we're in class, we'll try to be as interactive as we can, and hopefully something that was clear to you might be something that you can teach to a student, a fellow student, who found that particular topic less clear. So please make sure you note what is clear and what is not so clear, and I look forward to taking your comments in class. See you in class.